Welcome. We continue from last time. We have already looked at the geodesic flow, which is a permutation on the frame bundle of a manifold. Finite, abstract, simplistic, complex, everything is finite. So we have a permutation of this finite set. And we see here, visualize this a little bit in 2 dimensions. In 3 dimensions we can draw that too. And what happens is these geodesic tubes, these are maximal simplices stacked together in such a way that the curvature is 0. So we have a notion of curvature also for k-dimensional simplices, and especially on the facets we can define a curvature so that the Gauss-Bonnet theorem works. This was something done last year. So here, when we take a cyclic polytope and put these maximal simplices together in such a way that it's curved, and there is a curve. And what we do is we take geodesics where this is not curved, where it's flat. And this works in any dimension. And what happens is this geodesic depends on the orientation. And this orientation of the simplices also defines us a notion of, like a frame. We have a base, the first point, in the total order gives us the base point, and then we have vectors, so to speak, which give us kind of a basis. And this is mapped into a new basis, and so we have a notion of parallel transport. If you have a tangent space here and a tangent space here, we go from here to here along a geodesic, there is a notion of correspondence, a covariant derivative. So it's very important to have that in the continuum, and in the discrete, the finite, this works also. I think this is a very, very good definition. The work was to actually give a good definition. And another problem, in general relativity, we have the geodesics, which is mass moves on geodesics. That's important, but also the curvature is important, and the curvature is, so the Riemann tensor is defined when we have sectional curvature. So the only thing which we really need to understand in the discrete is curvature for 2-dimensional sheets. So we need to define a geodesic flow along in a 2-dimensional direction. That's also very natural. We can look at the bones. So what we have is a bone is a q minus 2-dimensional simplex. So in general relativity, this Recke calculus, a numerical method, this is important there, that you take a triangle of the triangulation of the 4-manifold, and then the dual, which is all the hypertetraeder which are hinging on that triangle, forms a circle. And that's kind of just follows from the definition of a manifold, because the unit sphere is a sphere. So and then a sphere in the sphere is a q minus 2-dimensional sphere. The sphere in the sphere in the sphere is a q minus 3-dimensional sphere. In every dimension, this dual bone is a 1-dimensional circle. So that's very nice. And we have also then a notion of direction. So this circle is here in the dual construct. The dual construct is actually best understood in the context of delta sets, which I'm very fond of, because what you can do in delta sets, you just reverse the order. To take this as a finite set of sets, and you have also a notion of face maps, and you just reverse the order, and you just define the derivative in such a way that the duality, Poincare duality, is trivial. So that's kind of the most natural way to see Poincare duality, which works if the manifold is orientable, meaning that you can assign orientation at every facet in such a way that they are compatible. And what I was working on this week is just looking at the construction of that geodesic sheet, something which exists in classical mathematics. You take a 2-dimensional plane in your manifold, and you let the geodesics move in every direction of that plane, and then you get a 2-dimensional sheet which is not closing up in general. There are caustics forming, and so it's a very complicated. This wave front becomes, after some time, larger than the radius injectivity, becomes very complicated in general. So that's in the discrete much nicer, because we have now a kind of a nice frame bundle, global finite frame bundle, and we can evolve in that frame bundle or the dual. So what we do is very, very concrete. So we start with a bone, which means we take a point, we take a direction right at the point. So this is not defining as actually a point. We could start at every of these points, right? These are all the facets, all the maximal simplices which contain this bone, which is a circle, and then we can start at every of these points. We can start at geodesic. That's what we do here. And then what we have is the key is geomark lemma. I'm fond of this, game here of geomark. So if you have in the dual is first of all just a graph, right? These are maximal simplices, and they are connected if they are sharing a q-1 dimensional simplex. And so when you have that, you can take the unit sphere here to intersect with the unit sphere here, intersect with the unit sphere here. What you get is it defines you a bone. And so that's what happens here. In this case, you actually have, when you take this path graph here, you get this bone. For every of the thing, you get just a bone which you started with. But if you now take this new direction, which is given by the geodesic, and you take these path graphs, you get new bones. And these new bones fit with, together they form a two-dimensional CW complex, right? So we have a two-dimensional cells glued together, and they all intersect in a triangle, which means that the dual is a triangulated manifold. So what we get is, so this is, this can close up. At some point you come back, but you might actually come back to X in a different orientation. That also happens with a geodesic flow, right? You can have the geodesic, you come and then you come back to the same triangle, but with a different orientation. And that happens also with geodesics, right? You can take a geodesic, classical geodesics, you can go around and you come back, but the direction doesn't match. So they intersect, these geodesics intersect in general, lots of times, in different directions. Of course, if it comes back in the same direction, then you have a periodic geodesic. So in the finite, of course, everything is periodic. All the geodesics are periodic. They close up after finitely many steps. And also this manifold, this is a two-dimensional manifold. By the classification of two-dimensional manifold, it has to be one of the known manifolds. But sectional curvature is no problem to define, because we have a notion of curvature for two manifolds. One of the questions is, what is the right notion of curvature? There are lots and lots of curvatures which satisfy Gauss-Bonnet, like, for example, curvatures which are located on the facets, we can take curvatures which are attached here to the points of the dual. So the question is, which notion of sectional curvature gives us a good notion? And a good notion is always a notion which gives theorems. Theorems which you know in classical mathematics, like, for example, if you have positive curvature, then you get the manifolds we know. There this classification of manifolds, which is believed to be complete, maybe not. We don't know whether it's a complete list yet of manifolds which have positive curvature, but it should at least give us the manifolds we know, like the projective spaces over the division algebras, or these exceptional cases. And also maybe that would be nice if in this framework one could prove that if you have positive curvature, so that then you have the original G has positive Euler characteristic, which is this is a conjecture of Hopf for even-dimensional manifolds, which is known in dimension 4, but not in higher dimensions. So that's it for today.